Started. Okay. So without further ado, let me introduce Professor Jinmin Wang from Chinese Academy of Science, AMSS Institute of Mathematics, who will tell us about higher index theory and its applications in scalar curvature.
Thank you, Xing, so much for your introduction. Now, I would like to thank the organizer for the invitation. So today I'm gonna talk about some more index theoretical picture and its application in the scalar curvature problems. And I would in the talk I will talk about this work with Bo Zhu. So this is mostly an introduction talk on this higher index theory because I noticed that in this conference, most of the speakers are from the geometry side. So probably this is more or less an advertising talk for this kind of operators theory applied to geometric problems. Okay, so let me start from some background. Okay, so the first background probably is known for most of us. So the classical Atiyah-Singer index theory. We start from a closed spin manifold, let me call it M. If we know the A homogeneous is non-zero, then M has no positive scalar curvature. This is actually a direct corollary of the Atiyah-Singer index theory and Legionnaires' formula. So the sketch of proof is that you consider the Dirac operator and you have Legionnaires' formula D squared is a rough Laplacian plus scalar curvature of 4. And so if you have positive scalar curvature, then D is invertible. But by Atiyah-Singer index theorem, the index of D is a homogeneous of M, which is a topological invariant. So if it's non-zero, if it's non-zero means that D is not invertible, and that will lead to a contradiction. And this theorem also has a rigidity part. If you have non-negative scalar curvature, then it has to be rigid flat. Because if it's non-rigid flat, you can do a conformal deformation and to make its scalar curvature strictly positive. Okay, so this is a classical result that use index theory of Dirac operator on this closed manifold to show that non-existence of positive scalar curvature. But this condition A homogeneous is non-zero is actually quite strong. It's of course satisfied for quite a few examples like Homer surface or Bloch manifold. This is a 4-dimension, it's 8-dimensional. But there are still quite a few examples where A homogeneous 0 and we also care, like torus or all-dimensional manifold, because A homogeneous only holds for, well, only holds for 4K. So other than 4K is all 0. So starting from this idea, Gromov-Lawson proved that no positive scalar curvature on torus using index theory. And this uses actually the so-called enlargeability by considering not the torus itself, but to its finite cover. And so, but we know that torus has 0 A homogeneous, so this is a very nice generalization of the original picture. But initial question is that what about other manifolds, in particular non-compact manifolds? Okay, so this is the first part of the background. And the second part of background is a problem of bottom eigenvalue of Laplacian. So it follows from the classical result that one can estimate the upper bound of the first eigenvalue of Laplacian via sectional curvature or rigid curvature for the work of Chigger and Cheng. And the recent work of Jinmin Wang tells us that this can also be done by scalar curvature. So suppose that we have a 3-dimensional manifold and scalar curvature has a lower bound negative 6K. And so if the manifold satisfies some topological condition, then we can conclude that the bottom Laplacian, that is L2 Laplacian, the bottom eigenvalue of the L2 Laplacian is less than or equal to K. Okay, so we start from the negative scalar curvature bound and deduce a control of the bottom eigenvalue of the L2 Laplacian. So here X is a complete non-compact manifold. The model example for this theorem is a hyperbolic space. The scalar curvature is negative n times n minus 1. Well, when n is 6, when is 3, it's just negative 6. And one can compute that the lambda 1 is equal to n minus 1 square root of 4. Well, in this case, when n 3 is just 1, so here it's just k. Okay. But actually, when the equality holds, one may not expect that the manifold is hyperbolic, because we also have this example. This word product metric, et squared plus cosine h of at to the 2 over a times the flat metric. If your a is in this range, one can show that scalar curvature is strictly greater than negative n times n minus 1, but the lambda 1 is exactly this. So this is almost hyperbolic, but not exactly hyperbolic, but still satisfy the two conditions. Okay. So far it's a geometric approach using harmonic functions. This theorem actually also have a Dirac operator understanding. It's a very early result of Davos. Tells us that if you have the same condition, scalar curvature greater than or equal to minus n times n minus 1 times k. But here, Davos work on the universal cover of closed spin manifold. So this is a non-compact manifold, complete, but beside of that, it may admit a co-compact free group action. And another topological assumption is that the A-hygienus is non-zero. This also appeared before in the Atiyah-Singer index theory. And with this condition, one can also deduce that the lambda 1 is less than or equal to the desired constant. The proof of this using the so-called refined Cartesian inequality, roughly speaking, use Dirac Laplacian to using Dirac connection to control the connection of functions. And the A-hygienus is non-zero is used to deduce that the Atiyah's L2 index of the d tilde on the universal cover is non-zero. And as a result, on the universal cover, there is an L2 harmonic spinor. And use this L2 harmonic spinor, one can deduce this lambda 1 bound. However, this result is actually not very satisfactory, because in the cases we really care about, like the hyperbolic case, the A-hygienus cannot be non-zero. Because in the theorem, actually Davos shows that if equality holds, then pi 1 is finite, and actually this k is 0. So, maybe, roughly speaking, it still somehow care about the flat case. But if you really work on the hyperbolic space, there cannot be an L2 harmonic spinor. That's too strong. So the drawback of this work is actually the choice of the index theory. So in this work, he used the Atiyah L2 index, but from this you can only work for this kind of like flat case k equal to 0, but cannot really go to hyperbolic case. To really work on hyperbolic case, one really need to consider some more refined index theory other than classical Fredholm index or Atiyah's L2 index. Yeah. So here comes the so-called higher index. And let me first state the result. So this is a work I put together with Bo Zhu, and we have shown that if you have a complete spin manifold with bounded geometry, if you have scalar curvature lower bound, then you can control the lambda 1 of L2 Laplacian, and provided that the Dirac operator has non-zero higher index. I will explain this condition later. Okay. So and from the next page slides, you might realize that, okay, this higher index should be a right candidate of the index theory that works, that is suitable for this kind of problem. Okay, and by the way, let me first explain the last sentence. We also have a rigidity statement. If equality holds, then the bad points where scalar curvature is greater than or equal to the negative n times s1 k plus a delta is not a net. Here I have quoted the definition. A set is a net if its our neighborhood covers the entire X. So in a very rough word, so the points with large scalar curvature, the bad points, has to be very sparse in X. So compare with the previous example I showed you, the scalar curvature is almost n times 1 at infinity, but the points that the point that violate this inequality is lying in the compact set. Okay, so before talking about what is this topological assumption, let me tell you first which case the higher index is non-zero. Here is a very limited cases because I due to the time and also I do well I do not have enough time and enough spaces to exhibit very many examples, but I've listed some useful cases where the higher index of D is non-zero. So the first case is the Gaussian manifolds, simply connected sectional curvature non-zero, less than or equal to 0, which already includes hyperbolic spaces and Euclidean spaces. And also the high index is actually a very coarse invariant. So you allow a small perturbation, a compact perturbation of the original manifold. So if you perturb the original manifold on a compact set, it still satisfies this topological assumption. And also, if you work on the AF or AH, asymptotic flat or asymptotic hyperbolic manifolds, then the condition still holds. So I'm not going to tell you the precise definition of AF and AH, but I'm pretty sure that whatever definition you take, the condition will be satisfied. And lastly, that also due to that the invariant is very coarse, you can also do a Lipschitz perturbation of the metric. So if you start from a Gaussian manifold and you can perturb a compact subset, you can also perturb the infinity by Lipschitz. Okay, so this actually implies the previous case. So if you ask a compact set by Lipschitz equivalent to a Gaussian manifold, where you not necessarily have sectional curvature less than or equal to 0, you will still have a non-zero higher index. And the last condition is more non-commutative geometry. So in our society, we mostly care about so-called geometrically contractible manifolds. Roughly speaking, these manifolds have no topology. So here's the definition. For any small r is a large R, that any R ball is contractible in its capital R neighborhood, where the small r and where the large R only depends on small r but independent of the base point. And for this manifold, if it satisfies some condition at infinity, then one can still deduce the higher index of D is non-zero. Here, the condition is like, for example, finite asymptotic dimension in the sense of Gromov, or if it can causally embed into a Hilbert space. I'm not going to explain these two coarse geometric conditions in details, but these are actually very weak condition and is satisfied for mostly the spaces you have seen. Okay. So I think from this incomplete list, I'm able to convince you that this condition of non-zero higher index is actually not very strong, and also it's satisfied by quite a few examples. In particular, it includes hyperbolic spaces. Okay, so then I think I still have to tell you what it is. I'm not going to really rigorously define the higher index, But I can tell you that it's really an analog of the classical Fredholm index. So let's first, so before telling you the rough definition, let me give you a brief history. So in history, when people consider non-compact manifolds, they actually start from universal covers, where M tilde is the universal cover of closed manifold, which admit a deck transformation of the discrete group gamma. Okay. Now you can lift the Dirac operator to a equivalent operator d tilde, and one wants to define the higher index of d tilde under the gamma equivalent case. So classically, this is defined or introduced in the Soviet society and in the name of Novikov and his distance for like Mishenko Fomenko to define this higher index using system bundles and finally generated projective system modules. And also Kasparov used Kiki's theory to define its index, which is more algebraic. And I think a breakthrough of this picture is Alain Connes' work in 1983. So he defined the cyclic homology and the noncommutative character and use this. So this is a very, very explicit construction of the higher index. And use this to prove some quite astonishing work for hyperbolic groups. And later, John Rowe gave another definition of the higher index by constructing a system algebra called the Rowe system algebra that can hold the higher index. I'm going to introduce this system algebra later, but I think this definition is quite nice because it not only works for universal covers, it also works for really non-compact manifolds without group action. Okay, so to introduce the definition of Rowe, I mean, let's first recall the classical Fredholm index. If you start from a closed spin manifold and a Hilbert space of the L2 spinners, and if D is a Dirac operator, we can consider this operator. F is D over square root 1 plus D squared. This is actually a functional calculus to make D a bounded operator, where the function x over square root 1 plus x squared looks like this. So this is 1 and this is -1. So this operation makes D a bounded operator. And you can also compute that f squared minus 1 is actually -1 over 1 plus D squared. And this operator is actually a pseudo-differential operator of negative order 2. Because the manifold is compact, is closed, then by the Rayleigh lemma, this small fd is a compact operator. And as a result, f squared minus 1 is compact, so f is invertible modulo this compact operator. And by the classical knowledge from functional analysis, we know that f is Fredholm, so that we can define the index of f to be the dimension of kernel minus dimension of co-kernel, which is an integer. Now, this is the classical picture of Fredholm index, but nowadays we have a more modern picture to view this in the point of view of system algebras. So this follows from a standard system algebraic result. Let B be a star-closed subalgebra of B of H. And A is an ideal. Oh, so actually A is important, but B is actually not very important. Okay, so you start from the operator T, which is invertible modulo A, like the F there. Okay, so one may ask if T is really, really invertible. And this does have a topological obstruction. And this obstruction is a class in the so-called K-theory of the A algebra. And with K-theory, the K-theory is a homology theory of system algebra. I'm not going to really define it, but it's very like the Atiyah's K-theory of vector bundles or the geometrical homology or simplicial homology of a manifold So that's just that kind of flavor, okay? And this class obstructs the invertibility of T. So that means if you know the class is non-zero, then T is not invertible. In particular, if you pick A to be compact operators, so B is not really important, okay? And here you can just pick to be the entire B of H. So compact operator is the ideal of B of H. Then any operator which is invertible modulo compact operator defines a class in the K-series of A. And you can show that its K-series just the group of integers. So actually, this K-theory class really coincide exactly with this Fredholm index. They are both integers and they're really equal. Okay, so far it's a theory of closed manifold. But if you move to non-compact manifold, things will be different. The key difference is that this operator is no longer compact. Because for non-compact region, you no longer have Rayleigh lemma. You no longer have a compact embedding lemma. So you only have F is the invertible modulo of this operator, but you don't know it's Fredholm. And actually, it's almost never Fredholm. Okay. Then if you are able to find a system algebra A that contains such operators, in particular the 1 over 1 plus d squared, then you can define a class in the case of A which obstructs the invertibility of F. Now you need to choose a suitable algebra A. A cannot be too small. If it is too small, then it's very hard to compute its K-series. If A is too large, you cannot capture any useful information. So you have to find a very nice thing in between. So to really find it, let's look at these operators, f of d. Okay. So this f of d has some very featured properties. So first, it's locally compact. So it's no longer compact, but if you restrict to some compact set, if A, B are compact, then it's really a compact operator. And second, that is that FD has finite propagation. So to see that, you can write FD as a Fourier inverse transform of this form. Its F hat is also a you can imagine it's a Schwarz function or even complex supported function. And in the Fourier inverse transform formula, this is e to the I cosine d, but this is exactly the wave operator. So if you want to solve a wave equation, you will exactly using this operator. And we all know that for waves, it has a finite propagation speed. So using the property of the wave operator, you can see that F, at least for a dense subset, it has finite propagation. So far is a construction for non-complete manifold. But if you really look at a universal cover, you may also notice that FD is gamma equivariant. So it commutes with gamma, the group action. Okay. We will talk about this later. All right. Now with this property, one can define the so-called row algebra. If you start from the Hilbert space of L2 functions, and let's consider the algebra of locally compact operators with finite propagation. And then we complete it to get a system algebra in B of H. Here, locally compact just means if you restrict it to a compact set, then it's a compact operator. And finite propagation means that if you restrict it to two sets that are very far away, then it's 0. So equivalently, you can understand this algebra as a completion of kernel operators. So if you start from an L2 function, and you can do this integral against a kernel, or against the integral kernel. And here, you know, that's actually a classical result that these kernel operators are automatically locally compact. And we want it to have finite propagation, which is say that k of x, y is 0 if x, y are far away. So very roughly speaking, this kernel function is only supported near the diagonal. And you can also use all kind of these kernel operators and do a completion, you'll get the same system algebra. Now, because we have already analyzed the property of the FD, then we see that FD really lies in this system algebra. And our capital F is invertible modulo this system algebra because F squared minus 1 is this form. So we can really conclude the following construction. So you start from the D and you do an F, then you can use the system algebraic result, you can define a class in the key theory of it. Okay, so here is what I mean by the higher index of D. And one really care about when this guy is 0 or non-zero. If it's non-zero, yeah, then there are probably many things we can say. Okay, so but to understand this class, we may first need to understand what is this system algebra and what is this key theory. And so unlike the compile operator, this key theory might be very complicated. It's a abelian group, but it might have torsion, it might have very high rank, it might also be infinite dimensional. So there's a conjecture by Paul Baum and Alain Connes relating to this system algebra. It's called Cauchy-Baum conjecture. Here I only listed a special case here. If X is a geometrically contractible manifold, here this definition I told you once before is just every small ball is contractible in a large ball. Then there's a map mu. This is an isomorphism from a K homology to the K theory of this system algebra. Okay, here have a footnote of what these are. So the K star of X denotes the K homology of X. So roughly speaking, it's generated by elliptic differential operators under some equivalent relation. And the map mu is just a map that to take higher index I've shown you here. So you start from elliptic differential operator and you do this functional calculus and then define an obstruction class in its case here. And the Cauchy-Baum conjecture said that this is an isomorphism. But actually, the left-hand side is quite computable. For this example, geometric contractible manifolds, the left-hand side is just a group of integers, which is generated exactly by Dirac operator. Okay. So if you want to know the index of Dirac operator non-zero on the right, well, if you know that X is geometric contractible, and you just need to check this conjecture, or even its injective part. If it's rational injective, then the higher index is non-zero. And this kind of rationally injectivity or even isomorphism has already been shown in very many situations in the work of using the work of noncommutative geometry and cost geometry. And so if the higher index is non-zero, then we can deduce our result to estimate the lower eigenvalue in terms of negative scalar curvature bound. And also, this also implies the conjecture of Shunyang Gromov-Lawson that the scalar curvature of X cannot be uniformly positive for geometric contractible manifolds. Because you see, if it's strictly positive, uniformly positive, then Dirac has a special gap, meaning that Dirac is really invertible. But this contradicts that the higher index is non-zero. Okay, so let me just make a summary of what so far happens. So the classical index theory talk about the curved manifold, but the the framework of noncommutative geometry can generalize to complete manifolds. And using the higher index, you can actually tell some geometric phenomena for non-compact manifolds. And the case where high index non-zero really covers lots of interesting examples that we'll care about. Okay, so far any questions? All right, and in the last two slides, let me talk a little bit about the rigidity part. So so the result is that if scalar curvature is greater than or equal to negative n times n minus 1 times k, then the lambda 1 is less than or equal to n minus 1 squared over 4k. Okay. So if the equality holds, we want to tell what happens. Okay. And our result is that the bad points cannot be a net. Actually, this follows from a so-called unique continuation property for nets. Here's the theorem we have shown. So suppose that y is a net in X, and let Ry to be its neighborhood. Then if you look at the Dirac operator and you do a spectral projection for a finite range, then you can realize that for any sigma lies in the range of spectral projection, so lying in the bounded range of spectral projection, its L2 norm on this whole manifold can be controlled by the L2 norm on this subset. So this is a so in other words, this is a unique continuation property. You can a continuation from Y, so from neighborhood of Y to the entire X is unique. Okay, and this theorem actually will prove use some classical Kalman estimate and generate to non-compact manifolds. And here I would like to give a remark for this theorem. So here we have used the fact that X has bounded geometry of X. Here the bounded geometry, the definition of bounded geometry is that there is some constant such that injective radius has a lower bound, and the derivatives of the curvature of the metric tensor has upper bound for k is equal to 1, 2, 3, 4. And in the proof of theorem, we really use fourth derivative. So we need the derivative to be at least 4. But we all know that to define curvature, order 2 is already very enough. So there's a natural question that whether one can relax this assumption of bounded geometry, the order of the bounded geometry. Okay. And okay, for really non-compact manifold, somehow this rigidity statement is sharp because we do have examples that is not hyperbolic, but still, but even scalar curvature not everywhere equal to negative n times -1, but still have the lambda 1 equality. But if you look at the universal cover, okay, M tilde, G tilde, then we probably expect that when equality holds, it should be hyperbolic. For universal cover, of course, you can still view it as a non-compact manifold and use the index theory I told you to define the higher index. And you can also include the group action on it and consider the so-called equivariant rule algebra defined by operators that are locally compact, finite propagation, and also gamma equivariant. If you add this condition here, you will realize that this system algebra only depends on the group gamma. So it has nothing to do with the original manifold M, okay, as long as M is a closed manifold. So now this geometric problem is completely converted to a somehow algebraic problem to study the group. If you understand the group very well, then you can understand this K-theory of this algebra or even the index of the Dirac operator. So in the case of universal cover, one can actually use both index theory. So you can use the higher index of the really non-compact manifold, or you can also use the equivariant version. If either is non-zero, you can still deduce the lambda 1 spectral gap. And if furthermore, if it's equal, and we can actually show that the scalar curvature exactly should be negative n times 1 times k everywhere. Because it's an equivariant metric. If you have somewhere scalar curvature, somewhere you have bad points, then the bad points is already everywhere, which is not possible. But actually, we do expect more. Like if we really have equality, can we see more about the rigidity, like the Ricci curvature or even the sectional curvature? We do expect that it's really hyperbolic space, but so far we do not know how to prove it. Okay, so this is last page of the site, and that's all of my talk. And thank you for your attention.
All right, thanks, Jinmin, for delivering a very interesting talk. And okay, again, questions from the audience. Okay, if not, maybe I'll say something. It's not like a question, it's like a half question, half comment. So in a rigidity case of this equivariant version of your theorem, probably I'm going to say something you know. So there's an old theorem of Brooke, which says that if you have a positive Boltonov spectrum on the universal cover, then the fundamental group cannot be amenable. So it already rules out a lot of cases. For example, you cannot admit non-negative rigid curvature, right? Because non-negative rigid curvature means the group is virtually abelian, which is clearly amenable. So I definitely believe that there should be more to say. Like in some sense, if the fundamental group is not amenable, it is already very close to like fundamental groups of hyperbolic spaces. I'm not sure if this is useful.
Well, I think we still have to admit that from non-amenable to hyperbolic, there's still a quite large
gap. Sure. Yes, of course.
Yeah.
Yeah, but what I'm saying is at least you can say that it cannot admit non-negative rigid curvature, for example.
Yeah, right. But I think we do expect that the rigid curvature is negative. By the way, here I'm not really say that k is possibly 0, of course, yeah. But
okay.
I guess I guess of course we're talking about the k is -1, right?
Yeah, sure. Yes.
We're really interested in this case. Yeah. So yeah, I think at least from the Dirac operator's side, probably one might need to look at the proof itself to see what kind of equation does this spinor satisfy. Yeah, to really deduce some equation of rigid curvature.
Okay.
Yeah, because if k is equal to 0, this is actually a direct proof. Only use Dirac operator to show us that it's rigid flat.
I see. Okay.
Yeah. But here, I think this is useful information. It's still more or less far away from what we're expecting. Yeah, thank you.
Okay, sure. Thank you. Any other questions or comments? All right, if all good, then let's thank our speaker again.
Thank you for your attention.
All right, so okay, I'm gonna stop recording.